James Webb just found a planet better than Earth. 99, 7% chance of life. It is July 1st, 2026, and something that happened in April of last year is still shaking the scientific community, and the argument itself tells you everything you need to know about how extraordinary this discovery actually is. A team of astronomers at the University of Cambridge, using data from NASA's James Webb Space Telescope, announced the detection of chemical signatures in the atmosphere of a planet 124 light-years away, that, on Earth, are produced exclusively by living organisms. They called it the most promising evidence yet that life may exist on a planet outside our solar system. The 99, 7% figure attached to this discovery is real, sourced directly from the data, and understanding exactly what it means and what it doesn't mean is the key to understanding why the story is one of the most important in the history of science, regardless of how it ultimately resolves. The planet is called K2-18b. It orbits a small red dwarf star in the constellation Leo, sits squarely within what astronomers call the habitable zone, the range of distances from a star where liquid water can exist on a planet's surface, and it is unlike anything in our own solar system. K2-18b belongs to a class of worlds called sub-Neptunes, planets larger than Earth, but smaller than Neptune that have no equivalent in our immediate neighborhood, and that turn out to be among the most common types of planet in the galaxy. It has roughly 8, 6 times Earth's mass, and about 2, 6 times Earth's radius, and based on everything astronomers have been able to measure, it appears to be what researchers call a Hycean world, a planet with a hydrogen-rich atmosphere sitting above a global ocean of liquid water. The conditions, based on multiple prior observations and confirmed by James Webb data, are consistent with the possibility of microbial life existing in that ocean. The two molecules at the center of the April 2025 announcement are dimethyl sulfide, abbreviated DMS, and dimethyl disulfide, abbreviated DMDS. Both are sulfur-based compounds. Both have very short atmospheric lifetimes, meaning they break down quickly when exposed to sunlight and need to be continuously replenished to maintain any detectable concentration. On Earth, the primary source of both compounds is biological. DMS is produced mainly by marine phytoplankton, microscopic ocean organisms, and is the chemical largely responsible for the distinctive smell of the sea. DMDS shares a similar biological origin profile. No confirmed non-biological process on Earth produces either compound in meaningful quantities, and no confirmed non-biological process in any planetary atmosphere studied to date is known to produce them at the levels detected on K2-18b. Here is where the 99. 7% figure comes from, and here is where the precision of the language matters enormously. The Cambridge team analyzed infrared light from K2-18b's atmosphere as the planet passed in front of its host star, a technique called transmission spectroscopy. As the planet transits, starlight filters through its atmosphere and different molecules absorb specific wavelengths of that light, leaving distinct chemical fingerprints. The team detected fingerprints consistent with DMS and DMDS at a statistical confidence level of 3 sigma. In statistics, 3 sigma means the probability that the detection is a random fluctuation in the data, rather than a real signal, sits at roughly 0. 3%. Flip that around. There's a 99. 7% probability that the signal is real and not noise. That is what 99. 7% means here. It is a confidence level assigned to the detection of the chemical signatures, not a direct probability that the planet hosts life. The distinction is critical, and the Cambridge researchers themselves were careful to maintain it. What the data shows is that something in K2-18b's atmosphere is producing these molecules. What that something is remains the question. The lead researcher on the study, Professor Niku Madhusudan of the University of Cambridge's Institute of Astronomy, framed the findings carefully but honestly in the paper published in the Astrophysical Journal Letters. His co-author, Mons Holmberg, a researcher at the Space Telescope Science Institute in Baltimore, was slightly more direct in comments reported by the Washington Post. Either we are looking at a new chemical process that we haven't seen before, or we are witnessing the first signs of biological activity outside Earth. Those two options are exactly what makes this announcement so difficult to sit with. One possibility is extraordinary and civilization-altering. The other possibility is that we are missing something in our understanding of atmospheric chemistry on a class of planet we have never been able to study up close. Both possibilities are scientifically legitimate. Neither can currently be ruled out. NASA's response to the announcement set the appropriate institutional tone. In a statement quoted by multiple outlets, the agency said that detecting gases produced only by life is difficult, even with Webb, and requires long observation times, and that the detection of a single potential biosignature would not constitute the discovery of life. That framing was deliberate. After the 2023 announcement of a potential DMS detection on K2-18b at lower confidence, which attracted enormous public attention and created expectations that proved difficult to manage, NASA and the broader scientific community are clearly determined to move carefully this time around. Caution turned out to be warranted quickly. Within days of the April 2025 paper's release, Jake Taylor of the University of Oxford published an independent reanalysis of the same underlying data and concluded that the detection of DMS and DMDS was not as statistically robust as the Cambridge team had claimed. Taylor's analysis, described in NPR's coverage of the controversy, suggested the signal strength in the data was weaker than the original paper indicated, and he flagged concerns about how the spectral fitting had been performed. The full raw data set from the Webb observations became publicly available on April 26, 2025, opening the door for the broader astronomical community to conduct their own independent analyses, and the ensuing weeks produced exactly the kind of scientific back and forth that defines how frontier discoveries get tested, challenged, and either hardened into consensus or quietly revised. A study published in Science Daily by researchers from the University of California, Riverside added further nuance, noting that while the Webb telescope probably didn't find life on K2-18b based on available data, the research does not rule out the possibility, and importantly, it outlines exactly how future observations could verify or definitively disprove the biological interpretation. That framing is actually more consequential than it might sound. Before April 2025, the question of whether K2-18b showed biosignature candidates was open. After April 2025, the question shifted to something more specific. What combination of additional observations, instrument configurations, and observation time would be required to push the confidence level from 3 sigma to 5 sigma, the threshold conventionally required in physics and astrophysics before a discovery is considered confirmed? 5 sigma means the probability of a false positive drops below 1 in 3. 5 million. Getting there on an atmospheric biosignature 124 light-years away, using a telescope that cannot directly image the planet's surface, is an enormous technical challenge, but it is now a defined target rather than an open-ended question. What makes K2-18b particularly compelling beyond the biosignature detection is everything else astronomers already knew about it before the April announcement. Earlier Webb observations, published in 2023, had already confirmed the presence of carbon dioxide and methane in its atmosphere, and found what appeared to be a notable absence of ammonia, which is exactly what planetary models predict for a water-covered world where the lower atmosphere is in contact with a liquid ocean. The data was already consistent with the Hycean world hypothesis before DMS or DMDS entered the picture. The April 2025 announcement didn't introduce the possibility of K2-18b being habitable. It added a new, biologically suggestive chemical layer on top of an atmospheric profile that was already pointing in a striking direction. The broader context of what Webb has been doing across its exoplanet observation program matters here too. A comprehensive analysis published in PNAS in September 2025 reviewed the state of biosignature detection in the Webb era and concluded that the telescope is genuinely capable of detecting biosignature gas candidates in the atmospheres of a small number of accessible habitable zone planets orbiting small stars. The paper was careful to note that Webb results in this area require what it called parallel interpretations, meaning the same chemical signal can often be explained by both biological and non-biological processes simultaneously, and that resolving between those interpretations may ultimately require the next generation of observatories currently in development. A second PNAS paper from April 2026, specifically examining the characterization of subneptunes with Webb, underscored that planets in the size range of K2-18b between Earth and Neptune are simultaneously the most common type of planet in the galaxy and the most scientifically enigmatic, precisely because we have no solar system analog to draw comparisons from. Webb itself continues to operate in outstanding condition. After more than 3 years in operation, its mirror and instruments show no significant degradation, and NASA and ESA both project it will continue producing science data into the late 2030s or beyond, well past its original design lifetime. That means multiple additional observation campaigns targeting K2-18b are not just possible, but planned, and each campaign will add data that either strengthens or weakens the biosignature signal. The community that was skeptical of the April 2025 announcement has not dismissed K2-18b as a target. They've simply demanded more data, which is exactly how science is supposed to work when the stakes are this high. The honest summary of where things stand as of mid-2026 is this. A telescope 124 light-years away found chemical fingerprints in a planet's atmosphere that, on Earth, only biology produces. The detection is real at 3 sigma confidence. The interpretation is genuinely contested. The planet it found them on is exactly the kind of world that planetary scientists had predicted might harbor life in its global ocean. The follow-up observations needed to push this toward a 5 sigma confirmation are underway. And the question sitting at the center of all of it, whether that signal means something is alive in the ocean beneath K2-18b's hydrogen sky, remains, as of today, unanswered. That the answer might not be no is already the most remarkable thing James Webb has ever shown us. There's a wider picture here too, one that gets lost when the debate focuses entirely on whether the April 2025 announcement was overstated. K2-18b is not the only world James Webb has been investigating for signs of habitability. In the years since Webb came online, the telescope has characterized dozens of exoplanet atmospheres, finding carbon dioxide on WASP-39b, confirming for the first time a carbon-bearing molecule in an exoplanet atmosphere using Webb's infrared sensitivity. It studied the rocky planet TRAPPIST-1c and found evidence it lacks a thick carbon dioxide atmosphere, narrowing down what conditions might look like on its more Earth-like neighbors, deeper in the system's habitable zone. Each of these results individually does not confirm or deny life anywhere. Together, they represent a systematic narrowing of the search space that is unprecedented in the history of astronomy. What K2-18b represents specifically is the first time in that larger process that a detected chemical signal has had no confirmed non-biological explanation. Prior detections on other worlds, water vapor, carbon dioxide, methane, have all been atmospherically interesting, but none produced the specific combination of being biologically exclusive on Earth, present at detectable concentrations, and requiring continuous replenishment in a way that is hard to explain geologically. DMS and DMDS satisfy all three of those conditions simultaneously, which is precisely what makes the April 2025 paper so difficult to dismiss, even in the face of legitimate methodological criticism. The critics challenging this statistical confidence are not arguing that DMS is present and has an obvious abiotic explanation. They are arguing that the detection confidence may be lower than claimed, which additional observation time can directly address. The telescope's longevity matters enormously here. With Webb now confirmed to have fuel reserves extending well beyond its original 10-year design mission, potentially into the late 2030s, the number of transit observations of K2-18b it can accumulate over the remainder of its operational lifetime is substantial. Each transit adds data. Each additional dataset tightens the statistical picture. If the signal continues to strengthen with each new observation, the argument for a biological source becomes increasingly difficult to explain away. If it weakens or disappears, that will tell scientists something important about the limits of current spectroscopic techniques on this class of planet. Either outcome advances the science, which is exactly what distinguishes a genuine scientific controversy from simple media noise. The honest summary of where things stand as of July 1st, 2026 is this. A telescope 124 light-years away found chemical fingerprints in a planet's atmosphere that, on Earth, only biology produces. The detection is real at 3 sigma confidence. The interpretation is genuinely contested. The planet it found them on is exactly the kind of world planetary scientists predicted might harbor life in a global ocean. The follow-up observations needed to push this toward a 5 sigma confirmation are underway, and with Webb now confirmed operational into the late 2030s, the number of transit observations it can accumulate is substantial. Either the signal strengthens with each new dataset and becomes increasingly hard to explain without biology, or it weakens and teaches the community something important about the limits of current spectroscopic techniques on this class of planet. Either way, the science advances. And the question sitting at the center of all of it, whether something is alive in the ocean beneath K2-18b's hydrogen sky, remains unanswered. That the answer might not be no is already the most remarkable thing James Webb has ever shown us.